L.7.5. Now we're moving on to a different type of polynomial, the two-term polynomials called binomials. This will work when the binomial meets the standards that we're going to set for it in today's notes. So when we have a binomial that has, first of all, what's really important, we have to look for subtraction. So we're going to look to see, is it a binomial where the two terms have subtraction between them? So before we would change it to add the opposite, is it a subtraction problem? And both terms are what we call perfect squares. So if we have subtraction and both the terms of the binomial are what are called perfect squares, then we say, you know what, this is one of those special binomials called the difference of two squares. Difference of two squares. Where did they come up with that name? Well, difference is the answer you get from a subtraction problem. We said it has to have subtraction. We said both terms have to be perfect squares, so we can also call them squares. So when we have the difference of two squares, we can use a special method to help us factor them. Examples of some special binomials. X squared minus 9. It has subtraction. How do we decide if the terms are squares or not? What does that mean? How do we say, oh, that's a perfect square? What makes a perfect square? Or can somebody give me an example of a perfect square? Four. 4 is a perfect square. Why? Because the square root of 4 is 2. Something times itself very nicely gets you to that square. So 4 is a perfect square. It is a square because 2 times 2 is 4. So anybody can give me an example of another perfect square now?
25.
25. Because 25 has a square root of 5.
So like, how about like 20? Like it's
How about 20? What do you think?
5, 4, is that?
Okay. Okay, 5 times 4 is 20. Do we all agree with that? The product of 5 and 4 is 20? Yeah, but if it's a square or a perfect square, both of those factors would be the same. So 5 times 4, 4 and 5 are not the same factor, are they? So they're two different factors. So that would not be considered a perfect square. 20 is not a perfect square.
100.
100 is, because it has a square root of 10, or in other words, 10 times itself. 10 times 10 is 100. Anybody think they can give me an example of a variable term that would be considered a perfect square? In other words, something times itself would get that. Yes, Ariel? X squared. Because what times what is x squared?
X.
X. Yeah, x times x. The square root of x squared is x. So we can even have variable terms that are squares. In fact, in our binomials, each of them, they are going to have a variable term. So I'm showing you right here, this is an example of a difference of two squares. X squared is a perfect square. 9 is a perfect square. It has subtraction in it. Is this one a difference of two squares? 4x squared. The minus, there's the subtraction, 25. How do you feel about 25? Is that a square?
Yes.
Yeah, because what times what gives you 25?
5 times
5. Okay. How about 4x squared? Is that a square?
Yeah.
Is there something times itself that would give you 4x squared? 2x, because 2 times 2 is 4, and x times x is x squared. So we would say 4x squared is a perfect square. So I guess that does qualify as the difference of two squares. It has a perfect square term at the beginning, a perfect square at the end, and it has subtraction. Okay, who wants to give us a third example then? Who wants to make up one for us that would be another good example of a difference of two squares? Juan's got a grin on his face, he wants to. Go for it, Juan. Huh? You don't even know what I want.
Subtract both of them?
No.
No, I don't.
Okay, can I get you to tune in then? Thanks. Okay, do I have someone who's gonna offer up an example of a difference of two squares? Stefan?
9x squared minus 4.
9x squared minus 4. Okay, everybody fill in the blank. He picked a good one. 9x squared minus 4. 9x squared is a perfect square. 4 is a perfect square. And there's subtraction.
Does it always have to be squared?
Does it always have to be squared? No. In fact, when we take some more notes tomorrow, we're going to find out that they aren't always squared. Cameron?
Would x to the fourth power be a perfect square?
So maybe you're trying to answer Trey's question already.
I was gonna say that.
Would x to the fourth be a perfect square? What do you think, class?
Yes.
Why?
Is x,
Because x squared times x squared is
X squared
x to
fourth.
the fourth. So it sounds like x to the fourth is a perfect square. So the answer to Trey's question is, does it always have to be squared? No, it doesn't have to be, does it? Okay, good. So how are we going to factor them? Well, here's what we're going to do. To factor them, we're going to find the square root of each term, because that's what we were just talking about. If you can find the square root, then you know it's a square, or a perfect square is another way to say it. So we're going to factor this binomial. In other words, we're going to rename it in factored form, just like we were doing with our trinomials. Well, each factor will begin with, I must need to calibrate here, I'm going to do that really quick. Each factor needs to begin with something and end with something. Well, when we find the square root of each term, those end up being what they're going to begin with. So each factor will begin with the square root of the first term. So when we find the square root of the first term, that's what our factors are going to begin with. And end with the square root of the last term, or the other term. There's really only two terms. But then we got to decide what kind of operation is going to go on in between them. So here's the deal. You start with a binomial, and it kind of feels like you don't get anywhere because you have this nice clean-cut binomial. It has two terms and it has subtraction between it. And then you end up with two binomials for its factored name. So it's kind of like you just made it a longer name is what you ended up doing. You have a binomial times another binomial that renames the binomial you started with. So you're going to get two binomial factors, each beginning with the square root of the first term, ending with the square root of the last term. One of them will have addition, and the other will have subtraction. So they're both going to start with the same thing, they're both going to end with the same thing. One's going to have addition in it, the other's going to have subtraction. So here's how you will show me your work. It's like how we're going to do here in our notes here. We have x squared minus 9, the one that we said was a difference of two squares. We have to show taking the square root of x squared. What is the square root of x squared?
X.
X. We have to show taking the square root of 9. What is the square root of 9?
3.
3. So we said both factors will start with the square root of the first term. Both factors will end with the square root of the last term. One will have addition, the other will have subtraction.
How?
Okay? And how? I mean, why does it just work this way? Why do you suppose? Why does it just turn out that you can just do it that way?
So you can just plus and minus with everyone?
Well, when do you think we can plus and minus with everyone? What standards does it have to meet before we can do this?
If it's subtraction.
If it's subtraction,
If they both have like the two numbers are like both,
perfect squares.
yeah.
Yeah, they're both squares. If they're both perfect squares, if both terms are perfect squares, and there's subtraction, then yes, this is what we get to do. Remember, how do we know if we have factored something correctly? How do we know? How can we check it out? Right?
We can multiply them and get the same. We can get what we had before.
Yeah, we multiply it out, and we see, does it get us back to where we started? So we have a binomial times a binomial. What method did I teach you
Foil.
first before we did anything else? FOIL, didn't we? We FOILed it. So if we FOILed this, let's see if it would work. F-O-I-L. So we have our first term, what is our F step in this one?
X times.
X times X, okay, because it's X plus 3 times X minus 3. So that's X squared, right? Okay, what's the O step?
X times negative 3.
X times negative 3, the outside terms. So that is what? Negative 3x. What's the I step?
3 times X.
3 times x, and that is 3x. And what's the L step?
3 times
3 times negative 3, which is negative 9. Okay. What happens right here?
They cancel out.
They cancel each other out. So we really only have x squared plus a negative 9, which can be cleaned up and become x squared minus 9. So you just see why one of them has to be addition and the other has to be subtraction? We need them to cancel each other out in the middle there. We don't want that middle term. We don't want it to be a trinomial. We started with a binomial. So when we FOIL it out, we should be able to get back to what we started with. Okay, so go ahead and do number 2 on your own. See what happens. What do you get? Number 2. Try it on your papers.
We do the same
Show the
stuff.
work. Show the same steps that we did in number 1.
Do you want us to check it?
You don't have to check it, but if you're done with it already anyway and you want to do that, take the time, go ahead and do it. And notice we're not changing these to add the opposite. We're leaving them like they are, and instead finding the square root of the first term, finding the square root of the last term. Then we use those in our factors with addition in one, subtraction in the other. Marky, what's the factor name for this one?
For the first step, I said X, and then 3.
3?
8.
Okay. So its factor name is?
X plus 8 and X minus 8.
X plus 8 times X minus 8. Square root of the first term, square root of the second term, other term, those are what start and end our factors. One has addition, the other has subtraction. Pretty slick, isn't it? Don't have to make a diamond, don't have to factor by grouping, just get to find the square root of the first term, square root of the last term, and set up our factors. Okay, here's one where a is not equal to 1, but it doesn't really make it any harder. We still do the same steps. We take the square root of the first term, which is 4x squared. What is the square root of 4x squared? 2x. We take the square root of the other term, which is 25. What's the square root of 25? 5. So both of our factors start with what? 2x. Both of them start with 2x. Both of them end with 5. And one has addition, the other one has subtraction. I guess also known as a negative to you guys. So 2x plus 5 times 2x minus 5 is the factor name for 4x squared minus 25. Now, why is it important that we know how to factor these? Well, coming up in chapter 8, we're going to have to learn how to solve quadratic equations. And being able to factor them is going to make it easier for us to solve them. Otherwise, sometimes you're going to be like, I have no clue what I can do to solve this, and you're saying, there is no solution, when there really is. So factoring is a really important skill we need for solving in our next chapter. 1.
What if there was no solution?
What if there was no solution?
Or
Then
is no solution?
if there is no solution, then we do get to put that. Sometimes there is no solution.
Put that
On our papers, yeah. This one, if we were solving this, if this was set equal to y or set equal to 0, we could actually solve this one. Okay.
What if you automatically know that it's not a solution? Like it's minus 26, you know what I mean?
Oh, there, so in other words, it's not factorable, you mean?
So
Okay.
can you just automatically put no solution if you already know?
You wouldn't put not no solution, what you would put instead, one is you put not factorable, and then you would give your reason. And it's because why? What would the reason be, one?
Just show you where.
No, because 26 is not a,
Yeah, square.
it's not a square, that's right.
So there won't ever be one?
Will there ever be that?
Like, there won't ever be an odd rate, like 26 or like 29 or something like that?
I mean, there can be, yes. When we're practicing this, will there be right away? Maybe not. But can there be? Absolutely. And then you'd have to say, wait a minute, I can't factor this one because that's not a square. 29 is not a square.
I guess today's assignment there's 4.
There are 4 of them. Okay.
So what do you say then?
So what do you say then? Well, okay, did you hear what I said to Juan? What were you doing?
Well, I was freaking out for it.
Oh. Juan, could you tell him what we're going to do when we say it's not factorable? He says, what would you say then?
No solution.
Don't, not factorable.
Because,
Maybe it's not a square.
yeah, so in his case, he was using 26. He said, what if it's 26 instead of 25? You would say, because 26 is not a square. 29, whatever, is not a square, okay? Okay, how about number 4? Is that one factorable?
Yeah. Yes.
Why?
9 and 16.
So- Can we take the square root of 9x squared?
Yeah.
So we would set it up like this. We would say the square root of 9x squared is 3x. Can we take the square root of 16?
Yes.
And that is 4. So this one is factorable because we could find the square root of both the terms. So our factored names would start with what?
3x.
3x. Both our factors start with 3x. Both end with 4. One has addition, other has subtraction. Does it matter which one gets it?
No.
No, order does not matter, remember, in multiplication, so it does not matter which one is subtraction, which one is addition.
Does it?
Because they both start with the same thing, they both end with the same thing, so it'll all work out in the end anyway. Smart.
Does it always have to, like, for like when you're the first step, you know how 9x squared and 16? For the 16, can you just say -4, or do you always have to do 4?
We don't want to say -4 because then we would have 3x plus a -4, and we'd have 3x minus a -4, and then we would just have to clean it up. So we're just making more work for ourselves. Okay? So I'm just trying to make it as short and clean as possible for you. Okay, any other questions? You've asked some good ones, you guys. Any others? Okay, then let's go to the back and see what we're going to talk about back here. Oh, we're going to do a couple more. Do you think we still ask ourselves the same question? Is the first term a square? Is the second term a square? And is there subtraction? Well, there's subtraction, so then I'm going to see if those are squares. Can we take the square root of 1? Why? In other words, there's nothing times itself that gives you 1. Oh, then on square root of 1 is 1, right? We're just looking for what times itself gives me that, radicand, that 1. And can we take the square root of 36x squared?
Yeah.
Okay, what is it? 6x. Okay. Now this is really, really, really important. Guess what? Just like the rules say, after you take the square roots, the factors start with the square root of the first term. They end with the square root of the other term. So what do these have to start with? No, 1. The square root of the first term is 1. They have to start with 1. They have to end with 6x. One of them has to have a subtraction. The other one has to have addition. Does 6x plus 1 mean the same thing as 1 plus 6x? Yeah. But does 6x minus 1 mean the same thing as 1 minus 6x? No. So we have to be careful. Order matters. So we have to follow the rule that says the factors start with the square root of the first term, they end with the square root of the last term, and one has addition, the other has subtraction. Okay, how about the next one? Let's go, it's got subtraction, so I'm going to start my work. Square root of 6x squared.
2.
Is 6 a perfect square?
No.
So, kind of like saying, you know what? Can't do. So we're going to say not factorable. And we just showed our reason right there. You can't take the square root of 6x squared and get a nice square root. Doesn't mean you really can't take the square root of 6x squared. I want you to believe you can. But you don't get a nice square root. And we want nice square roots. So we're going to say it's not factorable, and what we did right here supports it. Is the 49 a perfect square?
Yes.
Yeah, but do they both have to be?
Yes.
Yeah, they both have to be. Even if one is and the other one isn't, the one that is not breaks it down and says, you know what, not factorable. Okay, this is a really important fact. I want you to put a big circle around it. Don't be fooled into thinking you can do the same thing with the sum of two squares. What does sum mean? Addition. So if you have two squares, such as in the example right here, it says x squared plus 4. X squared, is that a perfect square? Yeah. Is 4 a perfect square?
Yeah.
But it has addition. It doesn't have subtraction. So here's what you might think, and there are advanced algebra students who do this. They say, you know what, that's a perfect square, that's a perfect square. I can say the square root of x squared is x, the square root of 4 is 2, so here's my factored name for it. Let's FOIL that out and see what happens when we do that. Let's FOIL. I got the spot there for us to do it. So if this is a factored name, it should take us back to x squared plus 4, right? So what's the f step? X times x, which is x squared. Good, we want that. O step, x times 2, which is 2x. The I step for that those factors, 2 times x, which is 2x. And 2 times 2 for the L step, which is 4. So now when we bring those down, does anything cancel out this time? No. So when we bring them down into an addition problem, we have x squared plus 2x plus 2x plus 4. What is that?
X squared plus 4x plus 4.
Is that what we started with? No. So then you're like, well, fine. I'm convinced then that I could just put subtraction between both of them. Yes, Trey?
If we can't do it if they're added, because then they'll both have multiplication signs. Then how come when we're subtracting, they both don't have subtraction signs?
Because if they both had subtraction signs, like let's do this one right here, Trey. Maybe this will answer the question. If we say that x minus 2 times x minus 2 should work because, you know what, isn't a negative 2 times a negative 2 a positive 4? I'm kind of convinced, you know what, it's a plus 4 in the end, so I'm thinking a negative 2 times a negative 2, that's a positive 4, so why wouldn't this one work? Well, the f step is x times x, which is x squared. Doing good so far. And then the o step, if we change these to add the opposite, like we're supposed to, the o step is x times negative 2, which is negative 2x. The I step is negative 2 times x, which is negative 2x. And the L step is negative 2 times negative 2, which, that's positive 4, that's good. Does anything cancel out?
No.
No. So when we bring it down into an addition problem, we say I got x squared plus negative 2x plus negative 2x plus 4. That is x squared plus negative 4x, because we got those like terms in the middle there.
So
And now I gotta clean it up. So let's see if now it'll look like it maybe. Still doesn't, does it? So is x squared plus 4, can we factor it?
No.
No. It is not factorable. It's a big fat no. So sometimes we do have polynomials that cannot be factored. It's just how it is. So we have to make sure that we follow the rule that says, you know what? If it starts with a perfect square, ends with a perfect square, and has what?
Okay.
And has what between in the
Addition.
binomial? No. Subtraction to start with. If it's a binomial that has subtraction, with a perfect square starting it out, a perfect square ending it, then I can use this process that we were using on the front and at the top up here. Then I can do that. But then I also come into this. Here's an example of a binomial. You know what? It's got subtraction. You just said if it's a binomial with subtraction, it should work. But I also said what? It has to start with a perfect square and end with a perfect square. And we discovered that it did not start with a perfect square. So we could not factor it. Okay, now here's what's going to happen though, because we're going to start running into times when things are not factorable. I'm going to tell you how many answers on the homework should end up not factorable. I'm not going to tell you which problems, but I'm going to say, oh, on today's homework you should find, I think Mrs. Preston already said there's 4. 4 of the problems that should turn out not factorable. Because here's what you don't get to do. You don't get to play lazy, look at it for a little bit and say, you know what, I think this one's not factorable. And then you do one, and then the next 2 are not factorable, and then you do another one, and you know, that's not how we're going to do our homework. You can only put down not factorable as many times as we tell you it should happen. And if once you've used all those up, you either go back and revisit some or figure out maybe the one you're on, maybe it really is factorable. Okay? Okay, so anybody have any questions that haven't gotten answered that you had yet? Okay, then let's get, I think you're going to probably need, where'd my, here we go. Turn this on.
Just wondering,
Yeah.
if we put not factorable, do we have to tell why?
We have to do like we did in the homework just now, or in the notes just now, where we showed the square root of 6x squared, and then we said, can't do it. Yep, you have to show the one that doesn't square. Yes, you do need loose leaf, right? You know what? I think you could probably sneak it on here if you want. Okay? So, let's get out, keep your notes out, don't put those away. And it actually says right in the directions how many are not factorable, so it's
So do we have to show up?
you don't have to foil, but that's called checking. But you do have to show what? What do you have to show? Let's look at our notes. What did we do for 1, 2, 3, 4, and 5? Answers, for that matter.
Thanks.
We showed this.
Yeah, that's called showing work, okay?
Isn't that the key?
I don't know. I mean, I'm not sure I can even understand you guys anymore. Okay, let's do number 1 together so we make sure we're showing the work we should show. What do you need to show for work for number 1?
The X. When you put that thing down, like
What's that called?
the little wing thing.
What's that wingy thing called?
Square.
Square.
The square root of.
Yeah.
The square root of
X squared.
x squared
Is
equals x. Okay. What's next?
Square root of negative. 4.
Just 4. The square root of 4 is
2.
2.
Okay.
That's called showing your work, and now you're ready to give the factor name.
The starter is X. The ender is 2. Well, one gives subtraction, the other one gives addition.
Okay. And there would be your final answer. Is that one factorable?
Yeah.
Yes, we just factored it. Okay, how many are not factorable?
4.
4 of them, yes. Okay.